Hello guys, it's Caribbean Bookworm, and in this video we'll be looking at a particular equation that pops up a lot in classical mechanics, and that is the Euler-Lagrange equations. And the Euler-Lagrange equation is basically an equation which allows you to do a lot of optimization problems in which you're interested in, for example, finding the minimum energy required for an object to travel from point A to point B, or you're interested in finding the minimum path that the object will travel, like say down an incline, and you do so without, for example, having to do, in the case of classical mechanics, force diagrams, without having to draw all of these very tedious free body diagrams and trying to deconstruct and decompose forces in different fashions. This formalism is a very powerful thing which is used in other areas of physics as well, and even and especially in modern areas of physics, by imposing things such as the Lagrangian and the Hamiltonian formalisms of mechanics. But those are a lot of jargon, and before we actually go on to the deep end, let's try to look at a simple problem, and from there on justify this need of the so-called Euler-Lagrange equation. So say you have an object that is starting at a particular point that we're calling point 1, and it wants to travel from point 1 to point 2. Now, there are various ways in which this object can do so. It can go through a path that looks like this, which, I mean, very straightforward, right? But it can also take a path that looks something like this. It can maybe do something like this, and it can do all sorts of crazy ways to get from point 1 to point 2. In our case right now, all of these are accepted. Basically, the object, let's say a person, starting at point 1, can travel in many different ways to go from, well, its location to point 2. But what is the optimal way in which the person can walk from point 1 to point 2? That is actually what we will be interested in, but before we do so, let's just look at the path that we have right here and look at it very closely. If we look at this path very, very closely, then we see that there is a smallest, you could say, increment that you can travel on this path. So for example, if it's a person walking, then let's say 1 footstep is the smallest step which the person can take on this path. Well, in mathematical terms, the analogous way of calling this smallest increment is something that we will denote as ds. And ds, if you want to know what ds stands for, in our case, well, we can think of ds as being this. I'm going to erase this bit right here. But we can think of ds as being this thing right here. This, let's say this line segment. We call it ds. And because our picture is drawn on a whiteboard, which is two-dimensional, we can say that it has a y component and an x component, which we will call respectively dx and dy. And you can consider it to be a right triangle. That means that if we want to find an expression for ds, then very straightforwardly, we can use the Pythagorean theorem to say that ds is equal to dx squared plus dy squared, and of course the square root of this, as per Pythagorean theorem. Now, one thing which we need to keep in mind is that this dx component is a very small change amongst the x-axis, and this dy component is a very small change amongst the y-axis. But there is a different way in which you can express this right here. And the different way in which you can express this is actually by taking note of something in mathematics known as a differential. And in order to give a footnote before I continue, for this video, all which I'm expecting you to know is some basic calculus, and specifically things like differentiating and integration, and especially differentiating using things like the sum rule, the chain rule, and also a little bit of multivariable, but not much. So for example, just knowing how to take partial derivatives is more than suffice. So in any ways, go back to the point, we can express actually, for example, dy in terms of dx using this thing called the differential. And that is basically, we can write dy as the derivative of whatever you have. Let's say this path right here is described by a function y. So let's say that this path overall is a function y of x that is dependent on x. So if I were to plot this in a random graph, you would see that you have your y-axis right here and your x-axis right here, and you have a particular curve which we call y. So yeah, let's say that we have our derivative of this y right here multiplied by dx, or derivative of y with respect to x dx. This is something known as a differential, and it's not exactly the same as a derivative, as you can clearly see right here. But another way in which you can kind of see how this makes sense is by using the Leibniz notation. In the case in which we use primes right here, that is the classic Newton notation. But Leibniz, which was the rival of Newton when it comes to inventing calculus, and there's a whole debate of who invented it first. But using the Leibniz notation, we can see right now that we have dy dx, so it's just a notation for the derivative in terms of like d notation, Leibniz notation, and you can kind of already see what's going to happen right here. Typically, you're not allowed to treat the derivative, even in Leibniz notation, as a fraction. But this kind of gives you an intuitive picture of what's happening there. Basically, if we think of this as dy over dx, like a fraction, and if we multiply by dx, then basically the dx's cancel out and you just get dy. So making the logic of this appeal and make more sense. Now I say this despite some people watching this already being familiar, because I personally, when I was doing classical mechanics, was not very savvy on what the difference was between the differential and derivatives and how you can go to the next step, which we're going to do right now. That is basically, if we can see that we can write dy as this expression right here, then we can write this in our expression right here as well for ds. That means the ds would be equal to dx squared plus y prime x squared multiplied by dx squared, giving you this following expression right here for ds. Now we can take actually the dx squares outside, leaving us with 1 plus y prime x squared, and that's exactly what we're going to do. Now that we have this, we can very easily take this dx outside of the square root, and leaving us finally with our final expression for ds, and that is 1 plus. Leaving us with our final expression for ds right here. So for the smallest increment in which you can travel on this path. Now, we have this in mind. What if we're interested now in the total path which person travels from point 1 to point 2? Now, if we're interested in the total path, then what we need to do is sum over these various ds's over the interval which you're interested in. So in this case, we're interested in summing over these ds's all the way from the state which is in at point 1 to its increment to state number 2. So if you are to write this out, and I'm going to erase some bits, this means that we will have to, in essence, if we're interested in this path, which we will call, let's say, L, if we're interested in the path L, then we need to sum over all of the ds's over the particular steps. But we can do this in a more efficient way by, instead of using summation, we use integration, since this y right here is a continuous function. So we can just say that, oh, we're interested in the smallest increments and summing all of those over, especially since we're interested in ds, which we literally said was like the infinitesimal small step which the person could take on this path. We say that, okay, we're taking the integral of ds from state 1 to state 2. All right, all fair, nice. Now we can substitute for ds the expression which we found right here, giving us a total path in this case of the integral, let's say this time not of 1 to 2, but of x1 to x2, since we're going to have this dx right here of 1. This, in essence, gives us the path which the person travels from 1 to 2. Now, this is an example of something known as a variational problem, and there are many of these in classical mechanics and just in physics in general. And this idea is very important for what we're going to do next. Because the next question now is, well, how do we know which one of these paths the person traveled? So he could have traveled this one, but he could have traveled this other one as well, and this other very crazy path. And we need to find a way to know which one he actually went across. And specifically, we're actually interested in which path would be the shortest one for the person to travel from 1 to 2. So if we're interested in the shortest path, then we need to actually try and do something that is very calculus heavy. And this is why it's kind of handy to know a little bit of calculus for this. So let's say in the case of a regular calculus scenario in which you have a function. So let's grab the simplest of case. Let's say you have a parabola that looks like this, and you're interested in where the parabola is at its minimum. So what is the extreme value of this parabola? That would very clearly be at this point right here, you'd say. And you'd be right. This means that in order to find out, let's say the parabola is described by a function f. In order to find out where the extreme value of this parabola is, you would have to look at what the x value of this would be. Let's call it x0. What this x value would be when you have the derivative of f with respect to x being equal to 0. So this gives you, of course, the you could say where the thing isn't changing anymore. And not only that, if you want to know if it's a minimum or a maximum, then you have to take the second derivative. If you take the second derivative of f with respect to x, and if you notice that it is bigger than 0, then you know that, okay, you have a minimum. The reason why this is I'd highly recommend you check a calculus textbook, but those of you who happen to know, is because of the inflection point and how it goes from a negative to positive inflection, etc., etc. But details aside, in essence, you want to know when the derivative is 0, what the x value would be, and then if you take the second derivative, if it's bigger than 0, smaller than 0, or equal to 0. If instead of a minimum, you have a maximum, such as in the case with this parabola, which I've drawn right here, then the main difference would be that basically when you have the derivative taken with respect to dx being equal to 0, the second derivative of the function would actually be smaller than 0, again because of the same argument with the inflections and such. So this tells you that, okay, now you have a maximum. And when you have neither cases, which can happen when instead of having this second derivative of f with respect to x being smaller or bigger than 0, when it is equal to 0, then you also have a point in which it is not per se a maxima or a minima, but the first derivative is still 0, and that perhaps would look something like this, where you have neither a maximum or a minimum, but you have this semi-stable spot of your function, let's say. These are all three possibilities, and actually in general we say that when you have the derivative, the first derivative being equal to 0, then you have something in your single variable function known as a stationary point. So this stationary point, you can kind of picture it in your head as being a point in which if you're a parabola and you're a surfer, let's say, going over this parabola, when you're at that maximum, you're basically standing still, and you can either go to your right or to your left. So you're standing still for a little bit. It can be the same case if you're at a minimum. Let's say you think of this as a well, in which case you have a ball rolling on that well. Basically, it can start rolling and then go a little bit upward, but then gradually start to stand still. And where it's gonna stand still is at that stationary point where you have a minimum. And of course, in the last case, which you saw right here, you have a semi-stable point in which maybe you have a ball that's standing right here on a hill, in which if you give it enough of a nudge, maybe it might be able to go over the hill. But if you give it a slight different nudge, it might go, well, actually more to under the hill, basically. So that's maybe an intuitive way of thinking about this. And now let's apply this to a more general context. So similarly to what we saw for single variable functions and just functions in general, we want to do this similar trick to find out actually what would make the integral which we saw, which was, for example, L, the path which the person traveled from point 1 to point 2, what would make this integral give it its minimum value. So in essence, optimize the path such that you can find the path that is, well, the most optimal, the shortest path, you could say, between point 1 and point 2. And for this, that means that basically we need to do a similar trick of finding when your integral is actually stationary, but you can already see the slight difference right there, that instead of having instead of getting a particular point like x0 where you have your extreme value, you're going to get a specific function that tells you, oh, this is the function which the thing will have if you have an optimal or shortest path. So that is the very slight difference. And when we're doing something like this, so when, for example, we're having, instead of in a regular case, we have a function of x being optimal when its derivative is equal to 0, this time we're having a function, something known as a function null, which itself has, for example, yx, and that derivative will be equal to 0. So basically, instead of having your input be a single number, you could say, this time your input will be a whole function in and of itself. Now let's try and work with this. So say you have an integral like the one which we saw before with length, but instead we're going to call it an integral that is defined as s instead of L. This integral, we say it's dependent on a functional, let's say, that encompasses y, which is itself a function of x, y prime, which is the derivative of the function y, and x, the position. So we have f be a functional that is dependent on the functions y, the derivative of y, and x. Okay, if we're taking the integral of this thing and we want to find this integral with respect to dx, for example, then we'd say that we want to take the integral from x1 to x2. So say we're going from one path, point 1 to point 2, of the integrand, which in this case is this whole functional expression right here. So yx, y prime x, and x, and of course the x. How do we even visualize something like this? Since this might be a very new concept. Well, this is where we can use a very nice picture similar to what we used before and introduce some slightly new parameters. So say you have, similar to as before, your x and your y-axis, and you have point 1 and point 2, and you have a very specific path right here that is expressed as y, well, y of x, so it's your function of x. You can have a path which is slightly different from this one right here. So let's say we have this right here. So we have a curve right here which I've drawn with thick line, and that is something which we will call in this specific example the right path, the correct path, and any other path which we have will be the wrong path to take. So path in this case would be the function, let's say, of yx. So y of x in this case describes the right path, but any other path describes something else. And in this case, let's say that the right path is something called capital Y. So capital Y, yx, that's the right path. This different path right here it looks somewhat similar to your arbitrary path yx right here. So we'll still call it capital yx, but instead of being equal to yx, it has an extra component which causes a slight deviation, because otherwise then it would be the same path as this one right here. So it has an extra component, an extra functional, which we will call eta of x. So eta, Greek letter, of x right here. This describes any other path that could be taken. Now this eta of x right here can be anything. It can be, for example, eta of x equals sine pi x2 minus x1 over something crazy, or it can be eta of x equals, like, let's say x squared plus 3x plus 2, or whatever else it may be, whatever functional you have right there. But the fact remains the fact that basically this, because you have this eta of x right in here, when you take the integral of this thing right here, you will obtain a larger value for this integral than you will for example, taking the integral of just y of x. Now you can notice already that we're talking constantly about y of x and such, or this big Y of x. And the reason we're doing so is that we can notice very clearly from the integrand that you have right here that is all dependent on x. So basically the integral which you're taking is of something that is mainly dependent on x, and hence why you can look at one specific say function, so y of x, one specific functional you could say, and just focus your energy on that for now. So that little side note aside, back to my story. When you have basically an extra term right here, an extra functional, the integral which you take of big yx, it's going to be bigger than what you get from doing just the integral of this right here. But there is something that needs to be true for all possible paths, so the right ones and all of the wrong ones, and that is basically that we're constraining our problem to which basically everything needs to start at point 1 and everything needs to end at point 2. So no matter which path you have, so either the correct or the wrong one thing that needs to be true is that at point 1 you have no deviation from the right path, and at point 2 you also have no deviation from the right path. So basically this term needs to be 0 at both x1 and x2. And that is very much what we will call our boundary condition for this particular thing. So we say that eta x1 is equal to eta x2, and in both cases, at both x1 and x2, eta should be 0. So this is the boundary condition which comes into play later and is very crucial for our derivations. So now that we have this, and we notice also that basically whether you have the right path or not depends on this eta term right here which we've introduced being equal to 0. You can express yx in a different manner, which actually makes the thing very much dependent on basically eta, on whether or not it's 0, and that's handy. We want that. So we can say now that y of x, or functional, is equal to yx plus alpha eta x. We've introduced another thing right here. I get that we're introducing a lot of new terms, but the reason why we introduced this new alpha term in front of the eta especially, particularly, is because then basically we can take into account that when we have the right path, this term needs to fall out, so alpha needs to be equal to 0 basically for this term to fall out when we have the right path. And this basically also means that we can write now our overall path of the thing, so the integral as a function of alpha as well, since basically whether or not you have the right path actually depends on what this value of alpha is. This means then that we can write our integral of s from x1 to x2 as being a functional f which contains, well, uppercase y, so for whatever this is, the derivative of y, and x, dx. Which means that we can write our integral like this, basically, where the integrals of x1 and x2 are, of course, the x1 and x2 that we're interested in right here. So if I label my axes, you can see that this will be x1 and this will be x2. And basically the thing which we write in our integrand is, well, basically we have a functional that is dependent on y prime and x. So we substitute the expression which we have right here for y, and we find its derivative to write for x. Basically, using the differentiation sum rule, we can see that, okay, we take the derivative of this, which is just y prime, and we take the derivative of this, which alpha, in this case, is a constant, means basically that we're left only with alpha multiplied by eta's derivative, so eta prime, and x. This is in essence, the path which we're curious about. Now take a note that this integral, well, now we mentioned that it is dependent on alpha. So in other words, we can say that this integral is a function of alpha in some sense of the way. And if, for example, alpha is equal to 0, then you have your optimal path right here. Now, there are very crucial takeaways right there. That is basically that 1, we can write this as a function of alpha. And 2, that when alpha is equal to 0, this path is at its optimal place. So that means if we think of this in terms of a very classic calculus problem and not a specific case with like calculus of variations and such, that means basically that if this was a regular function of the path, that when we take the derivative of s with respect to alpha, then we should find that ds with respect to d alpha is equal to 0 at alpha equals 0. Because that is what we basically said, that when alpha is equal to 0, this term falls out, so you have the correct path. And you have the optimal path as well. You have a stationary path. So in order to get the alpha, we're interested in taking the partial derivative of f with respect to alpha, the thing that is inside, the thing that is the integrand inside the expression of f. So that means basically that we will have the alpha. That means that our first step is that we have to take the partial derivative of f with respect to alpha. If we do this, then we actually have to do two things. We have to take note that we're doing partial derivatives. And second thing is we have to do the chain rule. And the first way that we can notice that, okay, something has to be done right here is that if we take the partial derivative of f with respect to alpha, and there are three things in here, not just one thing, but three things, we have to first look at this first part right here and take the partial derivative of f with respect to this first thing right in here, and that is in essence y. So we have to take the partial derivative of f with respect to y, and then we have to multiply by the derivative of what's inside right here with respect to alpha. So if we do that, basically we have one term which has alpha right here, and one term which doesn't have alpha. So that falls out, leaving us basically with eta. So we have the derivative, the partial derivative of f with respect to y multiplied by eta. The second thing which we will now have is, we will now have to do the partial derivative of f again, but now instead of taking it with respect to y, we have to take it with respect to the second thing right here, which is y prime. So we take the partial derivative of f with respect to y prime, and now we have to, again, because of the chain rule, find the derivative of what's inside here with respect to alpha. That being this only term right here, and very similar to what we had before, this falls out, and this leaves us with eta prime. And then thirdly, we have to basically find the partial derivative of f with respect to x, and then multiplied by the basically by the whatever's inside right here with respect to alpha. But because the derivative of what's inside here with respect to alpha, there is no alpha term, so you're just gonna get 0. Then you have 0 multiplied by this term right here, basically meaning that this falls out, and we're left with only two terms in our expression. So these two terms right here can help us, as we can substitute it now into our expression for ds with respect to d alpha. Now, finding an expression for partial derivative of f over alpha is actually perfect, because that is exactly what's happening when we are taking ds with respect to d alpha of the thing which we had. So basically, we're taking the derivative with respect to alpha of the integral of x1 to x2 of the functional f which depended on y, y prime, and x dx. you can take this operation like symbol into your integral, which basically means that ds d alpha is equal to the integral from x1 to x2 of your partial derivative of f with respect to alpha multiplied by dx. Now, knowing that this is the expression for ds d alpha means that we can actually substitute what we found right here into this expression right in the integral sign. Basically, having this expression right here, we can now do one last bit of trickery, and that is basically if we know, for example, that the integral of this is equal to taking the integral of this first part plus the integral of the second part by the same interval, just by the rules of integration, then we can look at the integral of this part alone and rewrite this in terms of just basically these two terms by using properties of basically the integration by parts. So if you remember integration by parts, and plus before we do so, I'm just going to write this separately as its own thing. So if you recall integration by parts, it says that if you have an integral of something, let's say u by dv, it is equal to u v minus the integral of v du. Now we can rewrite this in order to find an expression for just the integral of v du, which will come very handy to us. And if we rewrite this basically means taking this to the other side and subtracting the integral of u dv from this side right here. So we move this to the left hand side, it changes the sign of this, v du, and then basically we now move this right here to the right hand side, meaning that we will have uv minus the integral of u dv. This is a very slight little bit of trickery, but that is done for the particular reason that now we can define our v and du in a manner which makes our calculations very straightforward and easy. And that is basically, we will call this eta prime right here, we will call it our du, we will call this partial derivative of f with respect to y prime, we will call that our v. And now it's a matter of just plugging things in. Using this expression right here, we can now see that if we have our integral of v du, then what we shall have on this side is uv. So basically u in this case will be the integral of eta with respect to x, which in the case of eta prime just stands for d eta over dx. So because eta was a function of x, so eta prime, then the integral of that will just be eta, giving us eta of x technically, and then our v is just this right here, so the partial derivative of f with respect to y prime. And this, of course, is taken within the intervals of x1 to x2. Now, the other term which you have is minus the integral from x1 to x2 of u, and u in this case is again eta, so eta of x, and multiplied by dv, which dv is basically the x derivative, because we're doing things with respect to x. It is basically dx of this thing which we have right here, which we call v, so partial of f with respect to y prime dx. So this has an expression, a very peculiar expression, which we can now see that can be simplified by noticing that basically the interval of this, so if we take this, where for the x values, so in this case we have eta right here, which is technically eta of x, can be written right here as well, eta of x. If we take eta of x2 times this minus eta x1 times this, we can now go back to our boundary condition in which we said that eta of x2 is equal to eta of x1, and in both cases it's equal to 0, meaning that in this case we have eta of x2 times this, which is a 0 times this, 0, minus eta of x1 times this, which is again 0 times this, So giving you basically an overall value of 0, meaning that this falls out of the expression as well, which is very nice. So in essence, then we are left with having this whole term right here, this whole second bit right here of ds d alpha being written as the following expression. And now that we have this, we can plug this back into this equation, and that means that we will obtain the following. Now, because the integral is taken in both cases with the same interval, so from x1 to x2 with respect to dx, it means that we can now bring everything together under the same integral sign, saying that ds d alpha is now the integral x1, x2 of all of this, which remember again that eta is actually eta of x, so we will write it like that now. So meaning now when we take everything under the same integral sign, we have this right here, and one last thing that we can do is take this eta x outside, since at both cases is the same eta x, and that gives us the integral from x1 to x2 of eta x multiplied by this thing right here is, well, at the end of the day, is equal to 0, since we said that basically when we want the optimal path, so the optimal or the stationary path, then we obtain a ds with respect to d alpha derivative of a value of 0, which means that basically this whole thing boils down to 0. Now, this is a very crucial thing, because in here we have this little bit of an expression right here inside bracket. This expression right here is what we mentioned earlier when we started the video, that is something that is known as the Euler-Lagrange equation. So if I can rewrite this again up here, this right here is the Euler-Lagrange equation, and this actually, very interestingly, has to be equal to 0 if we're interested in obtaining a stationary path. The reason for that might not be as obvious, but one thing that we can keep in mind is that eta of x should be able to obtain any value. So at the end of the day, it should be able to be something that has a positive, negative, or a 0 value. So by that means, if we have our eta of x, which can be any value, at the end of the day, then the only thing that should always be a 0 value in order for this whole thing to be true, so that the derivative of s with respect to alpha is 0, is this particular thing in the bracket right here, which is the Euler-Lagrange equation. And you can even try and playing around with this. I obtained this step-by-step, you can say, proof of the Euler-Lagrange equation by using the Taylor book, and he explains not with equations but in a very wordy way in which you can test and see whether or not this holds. And that's basically if you take a same sign value for these two, so let's say this is a positive integer or a positive real number, and this is also a positive real number, that means that this integral right here is going to give you, well, a positive value. And if that is the case, then that means basically that the derivative of s with respect to alpha is not equal to 0, which in and of itself is a contradiction. So the thing which I just described right there is basically a basic method of proof of contradiction, in which you can try and see whether or not something is consistent or not. And in this case, if you take a non-zero value for this thing right here, then you obtain a positive value for your derivative, which means that for some reason the stationary point at which, or what's supposed to be the stationary point of your path s, has a non-zero value, so it's not stationary, which makes no sense. So for that, this right here has to be equal to 0, and it is at the end of the day what is known as the Euler-Lagrange equation. And I've started to mention earlier in the video some of the reasons why this Euler-Lagrange equation is really useful, but it is a very powerful thing for classical mechanics, because this means now that you can just have something be defined as a function. Let's say you can have a function for your force or a function for energy as well. So instead of dealing even with forces, you can just ignore forces completely and just deal with the energies you have for your particular system. And you take this partial derivatives with respect to, for example, instead of with respect to y, you take its partial derivative with respect to, say, angle or something else, and you can still obtain what you need. Oftentimes in classical mechanics, this equation is written in this manner. Instead of having the y's, it is written with qi, the time derivative of qi, which the time derivative is often indicated with a dot right here, and instead of dx we have dt right here. And you can even, instead of having your functions right here, you can use something defined as the Lagrangian, which the Lagrangian stands in essence for the kinetic energy minus the potential energy of something that you have. And if you do this little bit of maths with it, then you can basically simplify very complicated problems into a way which is very easy to grasp. And this qi right here, which you see right here and here, actually stands for something called generalized coordinates. So instead of dealing with, for example, coordinates of x, y, z, well, you can deal with those, but generalized coordinates means that you can express, say, one thing in terms of another thing, and you can also basically, you look at the degrees of freedom instead of looking at like, oh, you have x, y, z, momentum, velocity, etc., etc. You can rewrite things like momentum in terms of other things. So that is what makes it very handy. This equation holds only for some constraints, so some boundary conditions of your problem, and particularly something known as holonomic constraints. But that becomes a whole video in it of itself, so don't worry about that. It doesn't hold as well for non-holonomic constraints, but again, if you're interested in classical mechanics, you can dive into that even more. But at the end of the day, the moral of the story is that this equation can be used to simplify problems such as a very complicated, let's say you have a ceiling right here and you have an Atwell machine, which is something that looks like this. You can have a problem that looks like a very complicated, like Atwell's machine scenario, in which you have these two things that rotate, with a bunch of, say, cables and such, and a block that's hanging off of it. If you were to do this with force diagrams and try to decompose all of the forces, like torque and all of those things, it becomes a hot mess. But if instead, for example, you're interested in how fast the ball is falling, you look at kinetic energy and try to use the Lagrangian, you can pretty much make your life much easier. Also, another problem that is deceptively difficult in the case of classical mechanics is having something like a double pendulum. So having something that looks like this, for example, in which you can have 2 degrees of freedom, you can have an angle of theta, and you can have an angle of, for example, phi right here. You can have 2 degrees of freedom. And the simple fact that you have 2 degrees of freedom means that if you want to do this in the sense of decomposing forces, you're going to have a bunch of trigonometric terms, which again makes it not as straightforward to work with. While instead, you can use something like Lagrangians or even Hamiltonians, which instead of having the kinetic minus the potential energy, the Hamiltonian is just the kinetic plus the potential energy. So in a lot of sense, it can almost be thought of as the total energy of your system. And because this is very easy and handy to work with, or much more convenient, you could say, to work with, it is often used in even more complicated formalisms of physics. For example, in quantum mechanics, the Schrödinger equation often uses the Hamiltonian, because the Hamiltonian encapsulates the total energy you can have on your particular, say, particle or whatever system you're dealing with in quantum mechanics. And a lot of times in quantum mechanics, the main problem is that you do not have continuous smooth functions. So if you have your plot of your energy over time or distance, then a lot of times it's not going to be the smooth function that you can have, but it can take basically discrete energies. And for that reason, you want to look at, for example, the total energy that you can have in that system and do operations onto that. Hence why the Schrödinger equation, in order to describe how something changes, say, time dependent or maybe even time independent, it contains and uses the Hamiltonian a lot. And even in things like particle physics, like you get with field theories, that oftentimes in order to, say, look at what generation of new particle is coming up in like the standard model of particle physics, people actually put new terms in something known as the standard model Lagrangian, which Again, it's the same concept of kinetic energy minus potential energy, but it just looks much scarier because the kinetic terms can be many different terms, and so can the potential terms be many different terms as well. So this idea of Lagrangian and Hamiltonian mechanics is something that it stemmed from classical mechanics, but it has uses all the way to modern physics, and it's a very powerful thing to learn if you're interested in pursuing physics more. And the reason why this Euler-Lagrange equation is so important when doing things like the Hamiltonian and the Lagrangian mechanics side of things is because basically a lot of times nature is trying to find the optimal path to do things. Nature is very lazy. There's a funny book which I haven't read it, but I'm very curious about it, that's called The Lazy Universe. I forgot the name of the author. I found the title funny, but I think the book, I briefly looked through it, it actually looks like a very good book for exploring exactly this. And it makes this concept a very important thing because, for example, light travels at the path of shortest time, for example. Light, if you try, even look in the Taylor classical mechanics book, you see an example using light that is something related to calculus of variations. You have, for example, if you're looking at the work energy theorem, if you're looking at the difference in kinetic energy, energy is not wasted in non-optimal paths. It's often done with exactly in its most optimal way. So for example, if you have a rock that is going through space from point A to point B, then actually nothing is exactly stopping it from traveling in this way in another fashion. So say from here, here, or another different fashion completely. It's only that basically when you use this Lagrangian, for example, formalism, or use the Euler-Lagrange equation, that you find that, okay, this is very likely the path which is going to take because it's the stationary path. But of course, what the stationary path looks like might vary. And even more so, despite, for example, nature opting to go the stationary path, and it makes our math even more complicated. For example, in particle physics, or more specifically in quantum field theory, or the first version of it, for example, the quantum electrodynamics, the physicist Richard Feynman actually came up with a formalism of quantum field theory that is called the path integral approach. There are two approaches, the canonical quantization and the path integral approach. You don't need to worry exactly about the jargon, but the path integral approach basically says something that instead of nature with light, for example, opting to go the stationary path, at least in terms of time, actually light travels all of the possible paths, so an infinite possible amount of paths, but it is when summing all of these paths over that you get basically the one which you observe classically, which is, for example, if light is reflected off of a mirror, then the one which you see with light just bouncing off in a straight line is what you obtain classically after summing up all of the possible paths which light do travel, technically speaking, in terms of, well, quantum field theory, which is very interesting because in that sense then you like kind of go off of the rail and say that, oh, instead of nature always opting to be lazy, it is that nature does everything, and then you condense that and you get the lazy version out of it classically. So you can go on a whole tangent with this, but in order to round things off, I will continue on with what I'm wanted to say in the continuation of the video before I actually noticed that I wanted to say something and place this in the middle of the video. That's why the board is clean. This can be a whole playlist in and of itself, but because I'm already occupied with Journey to Relativity, I'm not going to dive too much into this, but I was interested in making this video for both people interested in my channel's physics content and also for myself, as I noticed that explaining this stuff helps me remember it very well, and I actually do need to kind of refresh my basically Euler-Lagrange and doing problems with Lagrangian mechanics, as it's going to come very useful for courses which I'm interested in taking. So I hope you found this informative, and if you're curious to see more videos like this, whether it be from the classical mechanics point of view or more from the mathematical, like calculus of variations point of view, let me know. I'd be curious to try and do more stuff like this, but of course my priorities now lie in finishing that Journey to Relativity video, as I have a playlist in mind which I'm also considering doing. So I hope you enjoyed this, and well, stay tuned for further videos. Bye.